from the part 1 session?
Sorry?
Like, do you have any questions regarding the previous training session or anything specific you want to discuss in this one?
Regarding the previous session, I cannot read the session after the training meeting. I think yeah, I I will read it again with this training session, and I will send you I will send the questions to
Sure.
your email.
Okay. So let's get started.
Okay.
So in this training session, we are going to discuss these sections. So first, I will explain you the regexes in visualism, the key regexes that we use very often, and how to use it in expression list or a script block. And then following that, I will list out the resources and what are the purpose of the resources, applications like that. And then also I will provide the detailed, like I will try to cover the main concept regarding this. And similarly, I will list out the hardware devices that we have in Visual Sim and the network devices also. And following that, I will share you some of the files that is there in the tool that will have a detailed description about these resources and hardware devices and network devices and all. So like, but in this session, I will explain it in the overview of these devices. And following that, I will explain the statistics that we can observe from the architecture setup block. So I will explain those, and then I will explain how to configure the power table. I will show you like how to design the custom power configuration, like in a custom design. How can you add the power feature, and how can you observe the power table? I mean the state plot changes and the statistics from the power table. I will explain those, and following that, I will explain a two tutorial, and I will try to build the tutorial in this session. Okay.
It's great. Yeah.
Okay. So let me open the tool. Okay, so let me open a new model and digital simulator. I'm going to set the stop time to 10.0, like 10 seconds, and I'm going to use a traffic and an expression list. Just in behavior. Also, maybe let us plot it. We already saw that the traffic can generate the particular signal in terms of data structures. So in this one, I'm going to generate, let's say 10 traffic, like every 1 second, there will be a traffic, and we are running the simulation for 10 seconds. So this one, I'm going to try some different regexes. Okay, so with expression list, you can do the some of the computations, like not for detailed logic, we will prefer the script block, but for simple logics like manipulating the data structure, we can use this expression list. So in this one, let's say we have already have for in expression list, whenever we going to use or update the data structure fields. Let me first explain, like show you the fields. If I run this model, I can see, okay, now the expression list is not doing anything, like this it is just sending it out. So we can see this, the data structure, like sending it we can see there are 10 packets coming out. So each of them has block, delta, DS name, ID, index, and time. We can manipulate this, or we can add more fields into this. In order to access those data structure, we have to use input dot, which is the port name, the expression that has input. We are going to tap the data structure in that port name, so input dot, and we are going to use a specific field. You can say delta, which is already there. We are going to set this value to 5. We can do that, or we can select random function. So we are going to say selecting the randomly setting a number for delta. So let's say if we are going to select a channel, then we can say, okay, this we have only 10 resources. We are dynamically allocating that, like randomly we are setting the channel value. We can use this delta to select the channel. So we can see the delta value. Okay, it is in random case. So this creates decimal value, that is a double values. So for integer we have to use iran. So we can see 8, 7, 3. So it is randomly it is setting the channel value or some value to this field delta. So similarly we can add or remove the field. So now we are using the existing field. Now let's say input dot, or so if we can just add this. So now these fields will be accumulated at the output of the expression list. So we can see width and the channel id. So this is one way. Also we can remove the fields within the channel, like within the data structure. So in that we can say we have to use remove fields. This is an inbuilt regex to manipulate this data structure. So in this one we have to use an array based format and select the field name. Let's say width. Now the width is removed. So this is one way of manipulating the data structure that is coming into this expression list. So and okay, so these have limited features, and about to explain the expression list, we can use conditions here, whether to send this data structure out or not, or based on some specific condition. Let's say I'm using some flag. So it is somewhere updated. It can be updated in the same field. Let's say I am putting the flag, updating the flag for every packet. I'm checking whether okay. After we calculate delta, I'm going to say if input delta is greater than 5, then we can set the flag. This condition checking will set the flag as true or false. If the condition satisfied, then the flag will be set. Otherwise, false. So based on this value, the flag, the expression list will send it out. So if I try this, sorry.
I think there are mistyping. It seems that there is mistyping of a condition.
Yeah, yeah, I corrected it. Okay, I mean, okay, mistyped it. So
And in
sorry.
up conditions, there is mistyping about flag.
Oh, okay, sorry.
Okay.
Thank you. Yeah, now we can see the number of packets is less. After 1 second, between the packets coming in at the second, third, and fourth, fifth, those packets were dropped or not passed out through this expression list. So these are one way of manipulating the data structure. Now let me try the script block. So this one is a powerful library in our visual environment. We can use this to design custom logic, custom designs. So and we can have a lot of freedom, like a lot of degree of independence in this. So how to use this is basic. We have two sections. One is initialization part, and another is the execution part. Just like after label begin, after this section, whenever the packet comes in to this script block through the port, it will start from this point, label begin. But whatever below this, like before this, is the initialization part, which will happen at the initial stage, like at 0.0. I can say just a variable. We can define any variable, like so this is defined at time 0.0. So if I say if some packet comes in, I can put conditions like if first pass, then send out. And one more thing is like we usually use port token to access the packet, like access the data structure. But with the expression list, we use input or the port name, exact port name. And this one, the port token is the preferred one. So this is one way, like this is just a general condition. So let me use, let's say we have an array here. Okay. Array one, and I'm saying 2, 3. I'm defining this at the initialization stage. Now I can manipulate this using some of the internal regex. I can say find the length, and I can append it, and I can say find min max, and I can do a find or search within that array. It will provide me an index. So these are like some of the regexes we use to manipulate the array values, some array data structure. So also we can use same field like the things I mentioned here. We can do all of these things in this script block. So in order to try this, like say I'm doing this, I'm just going to append this array in the data structure. Let's say port token dot. And one more thing is, in order to run the model with script block, you have to save the model. For like expression list and all, you don't have to save the model. You can just run it. So I'm going to save it. I'm going to create a local folder here. Now, if I run it, I can see the array values getting added. And one more thing is, we have to say we should have unique name for this script block, because we can use multiple script in the single design, and each can have a separate functionality. So we have to use right click and customize configure. Here we have to select name for that. So if say this is one is processing one, then if we have another block, then we have to give the proper name for that. So with the expression, like with this one, we can use single, this is a single dimensional array I tried. We can even use multi-dimensional array. I can use define it, or I can use a regex for this. New array 1 comma, sorry, 10 comma 2. Now this one is going to, let's see how it is going to look. So it is creating new array. You can see here we have created 10 index, like array of size 10 with values 2. So that is the exact meaning. Like the first one is saying what is the size of the array and what value it is going to be. We can even use irand of 1 comma 10. Then it will create, for each values it will create some random values between 1 and 10. So this is an example. This will be very useful in designing some specific complex like architectures and all, even for cache or memories or some specific implementing a specific algorithm. We can use this type of regexes. So, and one more thing I have to show you is that the expression evaluator. So in this one we can see there is a let me open it. We can see in the top section new model, open model, text editor, and expression evaluator. We can also click on this one. We can have a UI like this. This will be like an evaluator for an regexes. Like say we can check this, like say, sorry, like instantly at each line we can do the calculation. So every line will be executed whenever we press enter. So va dot append, what's the array structure like, and then b equal to a. Then we can dynamically create the variables here. Similarly with script block, you can dynamically create the variable, and the similar to the data structure, like we dynamically adding the fields. Similarly we can dynamically use the variables in that. So this expression list will be very helpful. We can use all the regexes here, and we can try like experimenting it before using it in the design. If we say we used it in the the expression list or script block, if we get any error, we don't know how to debug it. We can observe it here. We can do the normal calculations like 12 plus 13. We can do anything. So this expression evaluator will be very useful for that. And one more thing is I want to show you where you can refer the documentation for this. As I showed you in the first training section, we have a third section, visual sim regex. Here we have the inbuilt functions, and in terms of sections, like for array specific to array, we have list of regexes. As I mentioned, this is a new array. We can use the formats, what is the field that is used, and how, like an example. Similarly, we have and how to initialize an array, math operations, absolute values, append, clear specific values like 0, 0, everything will be clear. Concatenate two arrays and finding common values in that array, common index, extract. Like we have different regexes for different sections. This is for array alone. And like for finding the values that is greater than or equal, less than, and we can see casting and some mathematical functions, data structure based one, like as I showed you, and the like removing the specific field or adding some specific field or checking whether the field is there or not, and writing some virtual value to this field. And then we have other functions also, like find and search to specific finds, and matrix based, and these are like application specific. Like we have more detailed one, like we have queues, resources, and all. For that these kind of regexes will be used. So user can use this documentation section, and within the visual sim regex will have all the details about the regexes. So this will be a documentation for regex. Okay, so following this, I will I will be starting with the resources. So do you guys have any questions so far?
Nothing yet.
Okay. So with respect to resources, the Visual Sim library have inbuilt functionality like a standalone blocks. These are so. For example, queue is a simple queue block which can hold the packets or and like say like a it will have a control. It will either like receive the packet and send it out, or it will hold the packet within the queue like a buffer, and based on the signal like a flow control signal, it will send it out. So we can use this queue as a resource, and it will be very useful in all the design. Similarly, we have resource queue as allocate, which is based on the number of resources available. So if we have like 10 resources at the time, and we can allocate it to specific resources based on the availability. So this is one kind of a resource mechanism library that is used in to allocate the input packets according to the resource availability. The server is one of the important function. Like we will use this to define any hardware execution, like kind of let's say an execution unit or some specific application, but we are emulating the delay of that. So this, let's say this is an particular hardware device, and we don't want to implement all the internal details. We can see if we send some signal into this, we can get some detail output at particular time. So when we design a logic or system at system level, we can use servers instead of like worrying about internal logic. We can just say, okay, this is the exact behavior of this, so we don't have to worry, but we are going to use the server to emulate the delay of that. So that will be used here. And time based resources, we have queues in terms of timing, like so user can use this time based resources to instead of a queue, like whenever like we have multi-dimensional queue, within the queue we will have uh, n number of queues, and we can use that to like we can allocate it to specific one. We have algorithms to that, like say first come first serve, and all we have an option in the queue itself, whether it's first in first out or last in first out, and we can select the queue, which queue it has to go, and what is the if the queue has reached the specific capacity, it will send it out, like it will reject the code, reject the packet. It will not be stored in the queue, and it will not be passed through the queue. So those that is one of the resources in the visual sim. And following that, we have system like power table is I think it is for for calculation. We will come into we will look into that later. So next one is the system resource and system resource extent. So that emulates similar to server. Server is like exactly one input one out. System resource is like when there is a multiple sources that is going to use this resource. Like we have 10 devices that is going to give signal to this, and it has to process one after another. So this system resource can be called by call a mapper. So mapper will send the signals to system resource, and it will process it. Once it is completed, it will process the next one that is waiting in the queue. And similarly, we have system resource external. Like what happens? Let's say an example of processor. We are sending a instruction to processed in the processor, and the mapper sent it to the system resource, and it will, let's say it is emulating the other functionality of the memory accesses. So if it wants to reach the memory like cache, it will send the signal to the system resource. Once this, and during that it will be on hold. It cannot process anything else. So once the system resource extend is processed and everything is completed, then a signal will be sent to the system resource. Then it will be releasing the packet, and it will process the next one in the queue. So those kind of application can use this system resource and system resource extend. And mapper is the one which will create a virtual connection with the system resource or any other device. Like we have multiple inbuilt libraries that use this like that supports mapper to send the signals. So that kind of a resource is there. And we have channel. Channel is to emulate the network channels. Like it will create internal queues, and based on the availability of queues, it will allocate the channel and pass these um, data like a transmission line or transmission of data. It will initiate the channel and send it out to the next one. Like it will emulate those data transfers, those kind of stuff. So as I mentioned, I will share the files that have the detailed explanation about these resources in the mail. Once the session is completed, I will share those files and location. So following this, these are the hardware libraries that is in Visual. So for a simple design, as a user can use the device interface, which is just an interface for the master or so say slave devices. So we don't have to implement entire functionality of it, but we are going to say, okay, this is what it will do. It will provide these kind of informations. Then we can use the expression list to manipulate those values, and then we will send this packet through the device interface to all of the like a major devices in the system, like AXI bus or processor or memory. It will be passed through that. So this will act as an interface for the particular device. So this will act as a hardware device as in a basic system where the internal implementation is not important. Okay. So following that, we have a hybrid processor. This hybrid processor is works on trace-based emulation, where we have user can provide the executed trace, and it will emulate those trace and perform the memory accesses, context thread switching, and entire entire application, entire processing of the processor in terms of pipeline stages. So this is not stochastic, but not cyclic, but in terms of its combination of both. A part of stochastic performance is there, and part of cyclic functionality is there. So it does not perform any branch prediction or execution or actual behavior execution. Nothing will be there. Based on the trace, it will perform the processor behavior, and it will send out the signals to cache or memory or DMA, whatever it is requested, like as it is configured. And following that, we have cache memory. We have both stochastic cache and cyclic cache. Stochastic cache does not have detailed implementation of the algorithms like prefetching or replacement policy and all. It will just perform hit or miss. Based on that, it will perform based on the stochastic cache has that functionality. If it's a miss, it will send it to the next cache or memory. But we have a circulated cache which has detailed functionality: the prefetching, replacement, write back policies, and inclusion policies, and and associativity configurations. Everything is there. So that kind of a detailed cache is also there. And we have memory controller and DRAM, which is a cyclic memory controller and hardware DRAM. The memory controller will perform the address decoding, fragmentations, command bus handling, and initiating the signals to DRAM banks to activate the banks. And similarly, DRAM, which performs activation and like bidirectional bus transfers. Those kind of cyclic level implementation is there. And as similar to cache, for DRAM, we have a stochastic DRAM, which performs like we have a stochastic configuration. We can say what is the read latency, write latency as a single value. But in a memory controller or DRAM, we can configure in detail like RCD, RP, what is the pre-charge time, row to column delay, and write latency, read latency in detail. We have the specific configuration for that. But in stochastic DRAM, we just have to say what is the read latency or write latency, and what is the time it will take for control, like memory controller latency. So that kind of a stochastic DRAM is also there when it will be useful for someone who doesn't know how to configure the memory controller DRAM in detail. Similarly, and we have in terms of interconnect devices, we have bus arbiter and bus interface, which is a basic library for building a generic bus. So we can say, okay, what is the how many ports it's supposed to be, and based on that, we can use bus interfaces, and we can say what is the speed, what is the width of the bus, and what is the best type of data transfer, and what is the algorithm, like first in first out, or like round robin, or we can also, it can also support custom algorithm. We have a few ports to enable the custom, like user can design the custom algorithm in the visual sim environment. And we have AXI bus, which is a standalone ARM based AXI bus, which is implemented as per the specification. And similarly we have PCI, which performs, which is again based on the standard technology. And we have separate DMA block, which performs the DMA action and using in presence of the processor or memory. In a complex SOC system, we have implemented the DMA. Those kind of logic is also. So far, do you guys have any question?
Not yet. Okay.
Okay. Following this, we have network libraries. In network libraries, we have node, which acts as a node uh, in the net. Like the node block will be utilized for implementing the node in the actual internet or network. So that will performs the retry like retry and the error correction checking. Those kind of functionalities maintained in that, and all other devices the connected to the network can be connected to this node. And we have routing table. So routing table defines what is the routing like routing mechanism. Like say this node is connected to this node through, we have the connection to the node 1 to node 5. So we can define the detailed connection for the routing in the network. And similarly we have layer table. Layer table and layer protocol are used in specifying the OSI layers kind of stuff. So we can say how many layers are there, like MAC layer, transportation layer, um, application layer. So we define those layers and we use the layer protocol to emulate those. Sorry, the layer protocol will be placed in place of the each layer, like OSI, like the MAC physical layer, MAC layer, and transportation layer. Everything will be configured using the layer protocol, and user can define say whether it is a TCP or a UDP, and they can construct the entire network design. Similarly, we have a multicast. So this multicast is to send the multicast signal or broadcast signal to specific devices. So we have the in terms of networking, and in terms of specific libraries, we have audio video bridging library. We have inbuilt design that form the exact based on the standard specification. And we have built TSN switch, which can be used to in automotive, like mostly in automotive networking. So user can connect this TSN switch using gateway or any other device to emulate the computation, like main devices like controller kind of stuff can be connected through the TSN switch. And following that gateway is there, which connects multiple buses, and similarly the TSN can be connected through the gateway. And CAN bus uses, we have also a CAN bus that uses as I mentioned, like it is a standard, it is implemented as per the standard, and we can use that to connect the sensors and actuators kind of stuff. So these are the list of network libraries in the visual sim. We do have few more, but I mentioned here the main libraries, like in this, as I mentioned, the resources, hardware, and networking. These are the main libraries, and we have multiple. We have libraries beyond this. You can explore this using the file that I sent later. I will send it. So far, do you guys have any question?
Where if a user wanted to use Ethernet simulation, but then how
Okay.
they can implement the Ethernet model?
So
Or
with respect to Ethernet, we have implemented the transmission layer. Like we have the implement the TCP/IP protocols and the scheduling kind of stuff, and how the transportation is happening, like how the physical layer, like mainly there is the physical layer. What kind of how the data structure or the packet will look like. What are the fields supposed to be there? What kind of checking has to be done? And how much delay will take for transfer through the physical layer from one node to another. So those kind of detailed implementation is done. We have demo models for that. I will share with you. Is that okay?
Okay, then is there also the example about the internet?
Okay, let me get that. So this is Ethernet based one.
Mm-hmm.
Let me open another model. Okay, this is based on TCP/IP and also the models and okay, these are based on system resources.
Mm-hmm.
So these are based on the existing libraries, the nodes. This is the node block that I mentioned, and they have used
Mm-hmm.
the TT like there is a TT. Okay, I have seen one model, but I'm just looking for that. So these are based on the inbuilt design, but it is not in detail. But we have built my one of my colleague did a detailed implementation of the Ethernet with TCP/IP layer protocols and all.
Mm-hmm.
You know this. Okay, I will find this from my colleague and I will share it with you in the following email. Is that okay?
Okay, yeah.
Okay. So do you guys have any other question regarding the libraries that we have?
No, there is no education anymore.
Okay. Okay. Following this, I'm going to explain the statistics from the architecture level block. And based on like we usually find these kind of statistics like throughput of each device and the latency in terms of delay, how much delay it was each device processed, and the utilization of each devices. A queue, server, everything will have provide the statistics like what is the utilization of that particular device in the entire simulation, and the buffer occupancy. Like if some queue have buffers, it will say what is the exact like at the time of printing the statistics. It will show how many packets are in the buffer, like in the input queue or something, and how many packets are processed, like how many packets enter the particular block and how many packets are returned or processed by the device. And we have device specific statistics like cache or memory controller. Those will provide details in terms of the cache will provide hit miss ratios and the number of write backs and evictions. Similarly, the network devices will provide some of this. application specific statistics actually. So let me open a model. For example, if I we have the bus habiter, cache, AXI bus, memory controller, and DRAM, and Cortex A53 processor, which uses the hybrid processor. So if I run this model, I can see I have the architecture setup. Like we have already using the architecture setup, and this text display connects to the two ports, the internal stats and utilization stats. There is a name mismatch. Yeah, now it is working. Okay, like I think this is a few complex model. I will let me check a simple model. Right. Let me open the SOC model now. So like I will come back to the statistics once it is completed. Let me explain the power section first. So with power table, we have seen like how to configure it like in terms of general and how it looks like. So with respect to power table updates, we have a regex called power update, and uh, we use this regex to take the value like say in a custom design. User can use this power update to say okay this particular device or application particular device is going to this particular state. We have to specify the power manager name here and the exact block name like what is a device name. This will say okay I'm going this particular block is going to active state and let's say standby state. Like these kind of updates will be sent to the power table through this regex. So based on this, the power table accumulates the value for according to each device, and it will at the end or during the simulation, it will calculate the total power consumed by the entire design along with the entire device in this system. So this is the regex that we use, and we have the standalone libraries like the queue servers and system resource blocks. Those will send direct information to the power table, which we don't have to worry about. But in terms of custom design, like say we are designing uh, a specific logic. So if we want to add the power feature, we can use this power update and few other regexes that I will show in this next section. It is still running. Okay, let me I will explain the statistics in the tutorial sections that we will build here. Okay. So this is a power example model. It has schedulers, like four schedulers are there, four system resources are there, and each of them is triggered by the mapper. So this emulates a four-core system. So if I run this, we can see it generates instantaneous and average score for each, and it also has there's a block to generate the temperature and heat with them. So in this one, we are going to see how to configure the power table. Like in order to define, like we can see that in the expression list, it uses like there is a core power, which is a parameter in the top level. So we define the core value, like core power value as based on these values. how many cores are there, and the DBFS multiplier, which is another parameter. So we defined a parameter with some value, and we use this to define the power values, like within the active state, what is the power of the active stage. So we use this expression list to define the expression here, and this value is utilized in this one. So we have defined standby as 0.01 and core power as 1/100th of the core power. So this is one way of using the expression list to define the so many expression regular expressions. So let me add another one. Like let's say I'm going to add a custom design in this one. I'm going to use a script block, and I'm going to say walk to, let's say, processor. Within that, I'm going to first pick of like we can say what is the block name, and what is the power manager name. You can use the values directly in the regex just for the clarity. I'm putting it here. So this manager one is related to this power table name, so which is called manager one. So I'm using this value here, and this are initialized. Let's say for a single stage, I'm going to go when a packet enters into this, I'm going to perform a particular delay. So for that, I'm going to say this particular device is going to update the state. Manager name, and we by default we have active state. We can send that as a string. Now I'm going to do 10 millisecond delay. After that, I'm going to change the power to standby. So we have a simple block here, and I'm going to add traffic. And let's say this for every 10 microsecond. Fixed value. So we have created this. Let us run this. So in this case, we have to update this power table first. Okay. And for example, I'm going to use the same details. And So this is one way for enabling or disabling the power. If the power table is there, that is the power manager name, it will be checked whether the power table is available in the device, like the top level. If it is there, then it will update the power. Otherwise, it will ignore that. Okay, let me rename this. Yes. Okay, so in order to explain the impact of that particular stuff we had, let me remove this traffic. So the system resources will not be activated with just power alone. We can see there's only we have created 10 for every 10 microsecond there will be a packet, and we can see the state change at the time 0. There is a packet which improved, like increase the value. The instantaneous value is at 67 66.5 per minus 4. So for each value, like for each input, we can see that it is going from standby to active, and then after some time, I have added 10 millisecond delay. So simulation is running for 32 milliseconds. For 10 milliseconds, it was an active state, and then it came down, and then we can see there is it came to standby state. Here it is not clear. We can see it came down to standby. After that, there is a packet waiting in the queue. So this again, as it is a new transaction, new packet, it went again to active state and processed till for another 10 milliseconds, and it came down, and another packet was waiting. So it improved the value to, like, increased to active, and then came down to standby. So we can see the state changes happening in this one. This is the power value as an entire device. This is now this particular custom device is only performing some action. So we can observe these changes in the power value. If I add this, we have already seen, like, with this scheduler, we can see the impact of other devices. So it is not just, it is a cumulative power, like it is not like for a specific device, for the entire disk system. Now we can see the cumulative power of the four cores along with the along with a custom design, a custom device. So this is one way of analyzing the entire power consumption in the device, in the system. We can also see the statistics related to this power, like we have enabled the state plot, and also we have enabled the write stats to file. So with this execution, we can find the statistics in the local directory. So let's say this model is located in demo and power, and yeah, I was using this multi-core DVS design model. So during this execution, it created a local folder and store, like, created the statistics. If I open this one, we can see the value, like the cumulative power and average power consumed for each device, and the total power consumptions of the same. So this way user can analyze the statistics. And one more thing is using the state plot, the state diagram. So if I open this, yeah. So for we can see the activity and state changes for each devices. Now in this case, we have scheduler 0, scheduler 1, scheduler 2, scheduler 3, and processor. So we can see these are being activated in a timely manner, but this is activated on every 10, like every 10 milliseconds. So only there is a state change in there is a three state change during the entire simulation. So we can even drag and select the specific region. So we can see the power consumptions of each stage. Like during this time, it was an active and it came down to standby. After some delay, the second packet started, and we can see it was active for all the time. During that, we can see other devices that were active. So here it was came to active and came back to standby within a short time. And here we can see it was active for these time slots. So user can use these state diagrams to understand the power transactions within each devices. And with the statistics, they can observe what is the cumulative and average power consumptions of each device and the total device, total entire system. So with respect to power, do you guys have any question so far?
There are no question about this. Very interested, and so
Okay.
I will I will try some power modeling.
Sure.
Yeah, following this example.
Okay. Okay. So this is regarding the power. Let me try some tutorials. Let me explain the tutorials first. I'm going to use this to, yeah, in this section, the documentation visual sim doc, we can see the second section, which is visual sim tutorial. And within that, we can see I'm going to explain the architecture exploration, and we will see the basic system, creating a basic system. So I will just first open a model, a new model, and within that, I will follow this first. So with we can see the existing models, we can refer for that. I'm going to follow this whatever mentioned in this one. So it will list out the blocks that will be used in this design. So we can see the digital simulator is needed. So which is there in model setup digital. So I'm going to in that, and then a traffic block which is in traffic and under the traffic library section. I'm going to put that. So I will bring all the library sections that are listed here. Expression list, and then you can see the text display is needed, and the architecture setup block which is in hardware setup, architecture setup. Following that, the processor block, the hybrid processor, which is in processor generator and processor, and an instruction set block, which is again in processor generator, instruction set. And we are going to use the stochastic RAM block, so which will be in memory. So in memory, the first one RAM is the stochastic one. So we have drag and dropped all the necessary blocks, and here it says connection. Regarding the connection, we have to connect the traffic block to the expression list. Okay. And following that, the expression block is connected to the instruction input of the processor. So input of the processor is these instruction in. So I'm going to connect these. And then it mentioned the connect the bus port of the processor to DRAM. This requires two connections, one of either direction. So these are the bus ports. You can see bus out and bus in. The ST-RAM is here. So the bus out is connected to RAM, and the return path is also connected. And then the text display is connected to the instruction complete port. This is the instruction complete port, instruction out. I'm going to connect the instruction, the text display here. So it says configuration for the blocks, setting the traffic to processor DS. I'm going to, as I mentioned, we have a lot of data structures. I have shown you the header one, that is a simple one. For a complex models with SOCs or processor, we use processor DS, and then the digital stop time. The simulation time is set to be 10.0, and the instruction name is in instruction set block to be my instruction set. This matches the name in the processor block. So the processor has processor instruction set name, which is my instruction set. We have to make sure this the name matches with the instruction set. Correct. And then in instruction set block, change the instruction IU add to add. The processor DS has a default instruction in A instruction. So this instruction, this field is will be available in processor DS, and it will have a default of this array. This value will be there in this field. So we have to set the instruction set for this instruction. So let's say the instructions that have list of the instruction and corresponding to specific execution unit. Like int one will use this, will execute these instructions. Integer two will execute these instructions. Three will execute these. So, but we are going to send only add instruction to this processor. So we are going to say add, and we are saying it will take only one cycle for execution. It will take one cycle to complete the execution. So now the integer one will perform the add instruction. So okay, now keep the default for the DRAM. So we will keep whatever the configuration is there as it is, and set the expression block to modify a destination a hop to the name of processor. So we will use these two fields to say this particular data structure is going to this particular processor. So we will say input dot a destination equal to the processor name. Here we can see the processor name is processor 1. We can use this. And there is one more field, which is ahop. Input dot equal to the same processor name. This is required for the processor to know the instruction is destined for itself. So now the configuration is completed. We have to run the model to see whether it works or not. So if I run this, we can see the execution is completed, and we have set only one packet, like because the traffic was generating single event at 1 second. So we can see only one packet is going into the processor and it is getting completed. So if I increase the traffic, say instead of single event, I'm going to say fixed value. For every 1 second, add instruction will be sent to the processor. We can see like 10 packets are completed. And as a second part of this basic system, we have adding bus. We are going to use the bus arbiter and bus interface. So it is going to be between the processor and DRAM. So let me drag and drop it. So the location of this, we can see the hardware device. Under that, the bus arbiter is there. And the bus interface. So this is a combination. The bus arbiter is a controller, and the bus interface is the port interface. So for single connection, single interface is sufficient. If we have multiple uh, connection to this bus arbiter, the bus one, we have to use similar interface like adding another bus interface and using these to connect some other devices. So in this case, a single bus interface is needed, and they have mentioned disconnect the DRAM, place the bus interface and bus arbiter on a board there. Connect the left side to bus interface to processor, right side to DRAM. So the left side is connected to processor and the right side to DRAM. And we can see this is the bus one. We have to make sure the name must be matching bus one, and here it says bus one. So these all bus interfaces will be is corresponding to this bus particular bus, and we have mentioned the port name. So this have port name one and port name two are the ports. So if I run this, we can see it is not providing any detailed input. It is just the same packets are getting processed, because the reason is this processor using the caches which are like 100% hit ratio. It is configured in such a way. So let me add hit ratio to this. Say 0.2, like very low hit ratio for iCache and every other cache, so that we can see the transactions to the DRAM. So in this one, the iCache and Dcache will be sending the request to L2, and this L2 will be sending the request to STRAM. So if I run this, we can see the changes in, but in order to observe the change, we have the tutorial will say viewing the system execution. So for this, we are going to add a timing diagram. Let me add this, which is in hardware setup. So this has default values because bus one, STRAM one, all of like default names. So by just drag and drop, we can run the model, and we can see the activity of the each device. So these are for register read, register write, and integer one execution unit, because we are sending add instruction that is in integer one, and those were alone being activated. Along with that, we can see the DRAM signals, the AXI bus reading and writing, like mean the bus data read and write, and the DRAM refresh and the DRAM read operations. So along with this, let me show the statistics for this. Let me connect this text display to architecture setup. So we can see the statistics in the half time, like for the simulation is running for 10 seconds. It is creating two samples, so at 5 seconds, and one more will be at 10 seconds. So in this, we can see the processor statistics, which are the utilization of the Dcache, floating point unit, integer one unit. We can see that we can see only the integer one is getting activated because no other instructions are getting is being sent. So other integer and other execution units are idle. The utilization of integer one and I1 cache and the entire processor utilization and the register read write utilization and SDRAM utilization. So this entire first section describes the utilization of each device. This is the for bus one, which is connected between the processor and DRAM. So specific statistics are like the delay, which is the latency of this particular device. It took 3.4 e power minus 8 34 nanosecond to as a maximum delay, minimum for every transaction in the entire run. We can see the number of IOs per second, number of packets came and came out, which is like at a single moment at outstanding there are two packets, and the buffer occupancy of the bus, which has 16 packets were as a maximum. It had 16 packets, and preempt buffer occupancies, like there is no preempt actions were there. The throughput, like the common things are like this: throughput, utilizations, number of packets entered and came out, and the latency of each devices. Similarly, other than that, as I mentioned, application like a device specific statistics also there. With respect to processor, we can see the context switch time, the D cache, high cache, and L2 cache hit ratios, and what is the stall time percentage is the if there is any stall. In this case, we don't have any stalls because our traffic profile is very simple, so there is not much of a hazard or stalling. And the delay, what is the latency taken, like the maximum latency task delay by this processor, and then the STRAM. So this says the again it is similar to the bus. We can see the latency, and then the memory used. This is application specific, like device specific, the throughput of this. And this is for the half time, like at 5 second we got the sample. Similarly at the 10 second time, when at 10th second we got this sample. So we have limited like devices. So this creates, as I mentioned in the before, the first part of the training, this will monitor the devices and observe statistics from each. So for these devices, it creates this stats, and we can observe the timing diagram, the activity of each device. So this is the first tutorial in the architecture setup, architecture exploration. We can see this is the basic system creation. So I will do one more tutorial, which is a cache tutorial. I will build this model and then explain it to you how to analyze the statistics for cache, AXI, and the cyclocular data. So for this, I'm going to, let me save this. I'm going to open a new model, and I'm going to use the digital simulator first, and I can put a similar like parameter called sim time. I'm setting this value to 1 millisecond. So we are going to configure the stop time using the sim time parameter. So these are done. Now let us use the traffic block, and I'm going to use the trigger traffic. It is to create the outstanding like continuous transactions to the memory. So I'm going to use this. Let me first bring all the blocks that are needed. I'm going to use this memory, which is I'm going to use in cache for, this is for iCache, and again one more for Dcache, and one more for L2 cache. In order to connect these, I'm going to use the hardware device, the bus arbiter, and the bus interface. As we have two caches, I'm going to use one more bus interface. So we have to use the DRAM to create a backup for this L2 cache. So I have the memory. You can see the memory controllers there, and the cyclical DRAM is there. In order to connect these two, I'm going to use the AXI bus, which is in interfaces and buses, AMBA, and the AXI is there, AMBA AXI. And for traffic of Dcache, I'm going to add another traffic, a trigger traffic, and an expression list for both. So let me assemble this model. I'm connecting this buses with iCache, similarly for Dcache. And now this bus arbiter, we can connect like the bus arbiter will make sure it will send the packet, like any source can be connected to the destination. So I can just connect the L2 in the top, and the Dcache can also use this path to connect the L2, and the L2 can be connected to AXI bus, the same port. It is a it's a multi port, and it's a single input port and output. It's a multi input output port. And with that, connect the memory controller and connect the memory controller to DRAM. So these are the ports for these first two ports for sending the control signals to activate or pre-charge the bank. These are to read and write the data from the bank, and this is the connection. Now with this, uh, we have to configure it. First, we are going to say what is the traffic. We have to use the processor DS because the cache and memory controller, those will be those will use complex fields. So which will be available in processor DS, and I'm going to say for every 1 or 10 microsecond. For every 10 microsecond, a packet will be sent. Okay, sorry. This one I will maintain the single event, and I'm going to use a loop to create a outstanding packet. So okay, so this one at 0.0, a processor DS will be triggered. This trigger traffic just whenever there is a trigger at its input, it will send the traffic using this processor DS. So I'm going to use the join block. Whenever the packet is getting completed, the next packet will be sent out. I'm going to use this relation block to connect this. Now only one packet, like only one outstanding packet will be sent to the instruction cache. Let me rename this. This is a beacon. This is L2 cache. So now for iCache, there is only one packet. A single traffic is generated, and for every once the packet is completed using the iCache, once it is finished, then the next packet will be triggered. So the same processor DS will be going to this iCache, and for Dcache, let me set so max 3, and I'm using fixed value, but I'm sending only 2 packets. So in order to create two outstanding requests to Dcache, so same traffic processor DS would be there. In the expression list, we can manipulate the data structure field. So input dot a destination we have to give the name of this cache. This, let me say iCache, and we are going to say a byte, which is the data that is going to be read or write. So let's say 16 bytes is going to be read, and we have to set the command, what kind of read, whether it should be a read or write. So I'm going to say read instruction. So for iCache, we will use this read instruction, and other than this, we have to say address. I'm going to put a random address, random 1, 8192. And similarly for dcache, I'm going to put a destination dcache dot a byte 16 what the command for dcache. Let me try different, like a combination of read and write. So I will say I'll use a ran function 0, 1. It will create a random value for every traffic. So I'm going to pick 0.4. So for 40% of the time, I'm going to send read request, and for 60%, I'm going to send write request. So this command, this condition, after this condition, we are going to put this value. So by default, if it is not, if nothing is here, it will set value as true or false. We can based on this condition, we can set the value for true. The first section will be assigned to this, or the second section. It can be either a string or a mathematical operation. It can be either any value or any boolean function. So input.get command is the address. So I'm going to again command. So now we configure the traffic. Now I'm going to configure the cache. It's at 1000 megahertz. The cache size is 8 KB, and the sense amplifier size is 64%. The block size is 64, and it is address based, that is cyclical one. And these are for stochastic one. For cyclical one, we have to configure the buffer size and total outstanding, which is it is a non-blocking cache, so we can say number of misses can go out to next level. The miss memory name. So following this, we are going to send it to L2 cache. So remaining, you can leave it as it is if you are a first user. So we have to make sure the miss memory name and must be matching with the next level cache. Here it is L2 cache. So whenever there's a miss, it should go to the L2. And remaining, user can configure speed, the cache size, sense amplifier size, bus size, what is the associativity, everything can be set. A number of prefixes and all can be configured. Similarly for dcache, I'm going to say dcache 1000 megahertz, 64 sense amplifier size, and the cache. The bus will be running at same 1000 megahertz. Okay. And we have port 1 and port 2 here. And here you have to say port unique name for each port. So port 3, port 4. And L2 cache is here. You can see it is running at 750 megahertz. and the 64-byte output sense amplifier. So it is an L2 cache. We can say 32 kb, and it is going to DRAM. So we can keep other parameters as it is default configuration. And the XI bus, we can say it is running at 1000, and the number of packets, read threshold and write threshold defines how many outstanding packet that it can uh, hold or perform. So for now, let's say 20. This is for slave, and for master, we can say 20. We have only like one master and one slave, so we don't have to worry about the remaining. The first master and the slave read write threshold is sufficient. And the bus width, we can say 64 bytes, and we have to configure the device attached to it. So in this case, the slave device is DRAM. So it says SDRAM, so it's a DRAM. So this device name must be mentioned in this one. Remaining can be left untouched for first users. And memory controller name, this must be same, and the hardware DRAM name must match with the DRAM name. We have to make sure the memory controller name must be matching and DRAM name must be matching. We can use default configurations here for now. This DDR4. So both memory controller and DRAM by default will be configured to DDR4. So this can be kept as it is. Let me save it. I'm going to run this model. Okay. Okay, so for these kind of devices, we have to make sure the architecture setup is available in the model. So the model is running without any issues. In order to analyze the model and observe whether the functionality is correct, we can add the text displays for, let's say, we have inbuilt features like for iCache, we have debugging ports and to observe the latency and throughput. We can add some plots here. So I'm using time data plotter 2 at L2 cache. Let us observe the latency. Similarly, the latency iCache, Dcache. This for 1 millisecond, and I'm trying for, okay, maybe it is running for a longer time. Let's say 1 microsecond is sufficient. And let us observe the statistics using the architecture setup. And these are sufficient for now. So very few packets have processed by the cache. So we can see, let's rename customize name. You can see the latency of each of them. For iCache, in order to see number of packets, you can see these many packets have entered the cache and processing time for each of them. Similarly for L2, for Dcache. So this is a view to observe whether the caches are processing correctly, and what is the latency observed for each packet. In order to observe the detailed statistics, we use the statistics from the architecture setup and say at 1 microsecond. Okay, so similar to the previous model, we can see the utilization and the specific stats for the bus. Like we have the bus one here, the specific statistics from the bus one. The maximum delay is 17 nanosecond, and the input buffer occupancies, the number of packets, the throughput in terms of seconds. This is MBS, like megabytes per second. You can see it is this bus one provided a throughput of 1032. It ran at 1032 megabytes per second. And then we can see the specific statistics from DRAM. So earlier we saw stochastic DRAM. This is a cycle accurate one. We can see the internal command queue occupancy, number of packet entered, the maximum occupancy at a single time, how many read bytes entered the DRAM, how many read requests, and the total bytes, the write bytes. There is not much of a write. Most of them were read. And also we can see the cache statistics from each cache. So L2 cache has a very like low hit ratio. Like most of them are like 94% of them are missed because we configure the traffic as random. We created a random address and it is not consecutive or there is no spatial locality. So L2 cache has low performance in this case, and we can see the number of packet entered. So 16 packet entered the cache, and sorry, 19 packet entered the cache, and within that time, 16 are processed and sent out. Similarly, we can see the eviction, number of write backs, and the throughput of the cache, like in terms of writes, number of write MBPS, and the number of read MBPS, and the utilization of the cache, like what is how much time it was active. So similar to L2, iCache and Dcache can be observed. You can see number of entered in this 9, and the number of entered packet is again 9. So along with that, we can see the statistics for the AXI bus. In this one, there is, as I mentioned, only as we use only single master and single slave, the throughput and utilization of those will be observed here. And it will also provide a lot of other details. We can observe that using the specific debug ports for statistics. It is sending the utilization and throughput. And the queue occupancy. We have the master queue, which is occupied for this 18 packets have entered the master port, and it was processed and sent out to the slave. Similarly, slave has processed and transferred the packets. So these are kind of statistics we can observe from specific devices. So this we can, as I mentioned, this is a single outstanding packet to iCache and two outstanding packet to Dcache. So so far, do you guys have any question?
No, that's okay.
Okay. So these are the two models that I plan to do a demo. Do you guys have any specific question or requirements in order to clear anything?
Okay, I think your training session were very useful to understand the visual scheme and how to model.
Okay.
Yeah. So yeah, that's great. Yeah. And
Okay. So
okay.
like,
What? Yeah.
are you guys interested in like getting more details about the power and Ethernet kind of stuff?
Actually, I'm interested in the power estimation, and
Okay,
yeah, but I think I need to try it once
okay,
in outside, and yeah, and I will tell you what we need to more information or guys.
okay. Okay, then like why don't you try the tool, and if you get any issues or question, if you get any error, if you face any issues, you can always contact me through mail. I will respond to you, and we can cover that. And if you have any specific requirement, like if you want to know more about this particular library or like power estimation anything, you can raise a question through mail. I will happy to, we can discuss about that. Is that okay?
Great, yeah, thank you.
Okay then. Okay, then I will send this slides and the models that I used in this training session through mail, and we can communicate further.
Okay,
Okay.
yeah,
Okay then. Okay.
yeah,
Thank you so
yeah,
much. We will
yeah,
talk.
yeah. Thank you so much, and have a good day.
Same to you. Thanks.